In the early years of the 20th century, the world of physics was undergoing a profound transformation. The classical understanding of the universe, with its deterministic laws, was being questioned and ultimately shattered by a new field of study, quantum mechanics. One of the central ideas that emerged from this revolution was Heisenberg's uncertainty principle, a concept that would forever change how we understand the fabric of reality. Werner Heisenberg, a German physicist, was one of the key pioneers of quantum mechanics. His uncertainty principle, formulated in 1927, introduced an entirely new way of thinking about the behavior of particles at the smallest scales. The principle itself is deceptively simple. It states that it is impossible to simultaneously know both the position and the momentum of a particle with absolute precision. In other words, the more precisely we try to measure one of these properties, the less precisely we can measure the other. But what does this mean, and why does it matter? To understand this concept, we must first recognize that Heisenberg's principle does not arise from limitations in our measuring instruments or techniques. It is not a result of human error, but rather an inherent property of the quantum world itself. In the classical view, we assumed that if we had a precise enough measuring device, we could pinpoint the exact position and speed of any object. However, quantum mechanics has revealed a much stranger reality. Particles exist in a state of probabilities, not certainties. Imagine a tiny electron zipping around an atom, constantly in motion. According to Heisenberg's uncertainty principle, if we want to know exactly where that electron is at a given moment, we must disturb it in some way, perhaps by shining light on it. The very act of measuring the electron's position alters its momentum, making it impossible to know both properties simultaneously with complete accuracy. The implications of this are profound. In the macroscopic world we experience every day, objects follow predictable trajectories. If you throw a ball, for example, you can easily calculate its position and velocity at any given time. These classical systems obey the laws of Newtonian physics, where certainty reigns. But in the quantum realm, uncertainty is the rule, not the exception. Heisenberg's principle suggests that at the subatomic level, the universe operates with a level of fuzziness that is fundamentally different from our everyday experiences. This principle challenged the deterministic worldview that had dominated science for centuries. Prior to Heisenberg, physicists like Isaac Newton believed that if we had complete knowledge of a system's state, its position, momentum, and other properties, we could predict its future behavior with certainty. This concept of determinism was the bedrock of classical physics. But the uncertainty principle showed that such precision is impossible in the quantum world. It is not merely a limitation of our technology or ability to measure, it is a fundamental aspect of nature. At the heart of Heisenberg's insight was the idea that observation itself has a profound effect on the system being observed. In the quantum world, the act of measurement alters the system in ways that are unpredictable. This is known as the observer effect, and it has far-reaching consequences for how we understand the role of the observer in science. In a sense, the uncertainty principle introduces a new kind of fuzziness into the universe. Instead of a neatly ordered world where everything is known with precision, we live in a world where reality at the quantum level is described in terms of probabilities. A particle's position might be spread out across space, with different probabilities associated with different locations, rather than existing in a single definite spot. Similarly, its momentum is not fixed, but can be described as a range of possible values. This uncertainty is not due to any flaw in measurement, but is intrinsic to the nature of quantum systems. To further grasp the significance of Heisenberg's uncertainty principle, we need to explore the fundamental relationship it has with other aspects of quantum mechanics. The uncertainty principle is intimately connected with the wave-particle duality of matter, a cornerstone of quantum theory. In this duality, particles like electrons can behave both as particles and as waves, depending on how they are observed. When we measure the position of a particle, it behaves more like a localized point, but when we measure its momentum, it behaves more like a wave spread out over a region of space. This wave-like behavior is captured by the wave function, a mathematical description of the probabilities associated with a particle's properties. The wave function provides a complete picture of a particle's quantum state, including the probabilities of finding it in various positions and with various momenta. The uncertainty principle can be thought of as a direct consequence of this wave-like behavior. The wave function that describes a particle's state is inherently spread out, and this spreading is what gives rise to the uncertainty in position and momentum. One of the key mathematical formulations of Heisenberg's uncertainty principle is the relation between the uncertainty in position, del tax, and the uncertainty in momentum, del tap. It is commonly expressed as dx, dx, dpha, dha, d, where ha is the reduced Planck constant, a fundamental constant in quantum mechanics. This inequality tells us that the product of the uncertainties in position and momentum is always greater than or equal to a constant value. In other words, the more precisely we try to measure one property, the less precisely we can measure the other. This relationship between position and momentum uncertainty has important implications for our understanding of quantum systems. It tells us that there is a limit to how much we can know about a particle's behavior at any given time. Even if we use the most advanced technology and techniques available, there is a fundamental limit to our knowledge of the quantum world. The uncertainty principle sets a boundary on our ability to measure the world around us, not because we lack the tools, but because the universe itself is inherently uncertain at the smallest scales. Heisenberg's uncertainty principle, though groundbreaking, was not without controversy. It stood in stark contrast to the deterministic worldview of classical mechanics and prompted intense debate among physicists. Albert Einstein, one of the most famous figures in the development of quantum theory, famously disagreed with the implications of the uncertainty principle. He believed in a more deterministic view of the universe, famously stating, "God does not play dice with the universe." Einstein felt that the uncertainty described by Heisenberg was merely a reflection of our incomplete knowledge, rather than an inherent feature of reality itself. However, over time, experiments and advancements in quantum theory have shown that Heisenberg's principle is not only correct, but it is central to our understanding of the quantum world. The development of quantum field theory, quantum electrodynamics, and other branches of modern physics have all built upon the foundation laid by the uncertainty principle. In conclusion, Heisenberg's uncertainty principle was not just a technical discovery, it was a revolutionary idea that fundamentally changed our understanding of the universe. By revealing the inherent uncertainty in the quantum world, Heisenberg forced physicists to abandon the classical idea of a deterministic universe and embrace a new way of thinking about reality. The uncertainty principle remains one of the cornerstones of quantum mechanics, shaping how we understand the behavior of particles at the smallest scales and providing a deeper insight into the very nature of existence. The uncertainty principle, while conceptually simple, opens up a universe of complex ideas that fundamentally alter our understanding of reality. It not only reshaped the landscape of quantum mechanics, but also catalyzed the development of new models and interpretations of the nature of particles, waves, and even the role of the observer. In this section, we will delve deeper into how the uncertainty principle connects with other quantum phenomena and explore its broader implications on the foundations of quantum theory and beyond. One of the most significant contributions of Heisenberg's uncertainty principle is its relationship to the wave-particle duality of matter. At the heart of quantum mechanics lies the idea that particles, such as electrons, can exhibit both particle-like and wave-like behaviors, depending on the experimental setup. This was a key feature of quantum theory, famously articulated through the double-slit experiment. When particles, such as electrons, are passed through two slits, they create an interference pattern on a screen behind them, just like waves of light or water. This pattern suggests that the electrons are not behaving as discrete particles but rather as waves that interfere with one another. However, when we attempt to measure the position of a particle as it passes through the slits, we disrupt this interference pattern. The act of measurement forces the particle to behave as a localized object rather than a spread-out wave. This phenomenon, known as wave-particle duality, is inextricably linked to Heisenberg's uncertainty principle. The more precisely we try to measure the particle's position, the less clearly we can define its momentum. The interference pattern fades when we measure the position, confirming that our very act of observing the particle has altered its behavior. This result demonstrates how the uncertainty principle is not merely a limitation of our measurement techniques, but a fundamental feature of the quantum world. In fact, the uncertainty principle challenges the very notion of objectivity and the passive role of the observer in classical science. In the classical view, an observer could study a system without influencing it. However, in quantum mechanics, the observer plays an active role in shaping the outcome of the experiment. This is a direct consequence of the uncertainty principle. When we measure the position of a particle, we inevitably disturb its momentum, and when we measure its momentum, we disturb its position. This observer effect suggests that the act of observation is deeply entwined with the state of the system being observed. It is no longer possible to think of the observer as an external, detached entity. Instead, the observer becomes an integral part of the quantum system, shaping its behavior in unpredictable ways. This raises profound questions about the nature of reality itself. If the act of observation affects the system being observed, can we say that a particle has a definite position or momentum before we measure it? According to Heisenberg's uncertainty principle, the answer is no. Instead, particles exist in a superposition of possible states, with their properties spread out across a range of values. It is only when we make a measurement that the wave function collapses and the particle takes on a definite position or momentum. This idea, known as wave function collapse, is one of the most debated concepts in quantum mechanics. It challenges our classical understanding of reality, where objects are thought to have definite properties regardless of whether they are being observed. The uncertainty principle also has a direct connection to the energy-time uncertainty relation, another key concept in quantum mechanics. Just as there is an uncertainty in position and momentum, there is also an uncertainty between the energy and the time over which a system evolves. This is often expressed as the dTMT, dot, where delta E is the uncertainty in energy, delta is the uncertainty in time, and Hg is the reduced Planck constant. This relation is particularly important in understanding processes such as particle decay and the creation of virtual particles in quantum field theory. The principle suggests that over short periods of time, the energy of a system can fluctuate, leading to temporary violations of energy conservation. This concept of energy fluctuations is a direct result of the uncertainty inherent in quantum systems and is crucial in understanding phenomena like the Casimir effect and Hawking radiation. The implications of the uncertainty principle extend beyond the microscopic realm of particles. They also have consequences for our understanding of the macroscopic world, although these effects are much less noticeable at larger scales. The uncertainty principle sets a fundamental limit on our ability to predict the future behavior of systems, particularly when it comes to chaotic or complex systems. This has important implications for fields like meteorology, economics, and even philosophy. In some ways, the uncertainty principle mirrors the limits of human knowledge. We may never be able to fully predict the future because of the inherent uncertainties in the systems we study. One area where the uncertainty principle has had a particularly profound impact is in the development of quantum computing. Quantum computers take advantage of quantum bits, or qubits, which can exist in a superposition of both 0 and 1 states simultaneously. This ability to exist in multiple states at once allows quantum computers to perform certain types of calculations much more efficiently than classical computers. However, the very concept of superposition relies on the uncertainty principle. As quantum computers evolve, scientists must grapple with the challenges of managing quantum uncertainty while trying to harness its computational power. Heisenberg's uncertainty principle has also influenced other areas of theoretical physics, such as quantum field theory and string theory. In quantum field theory, the fields that permeate space are treated as quantum systems, and the uncertainty principle governs their behavior. For instance, it explains why the vacuum of space is not empty, but instead teems with virtual particles that pop in and out of existence. These fluctuations in the vacuum are a direct result of the uncertainty in energy and time, and they are essential for understanding phenomena like the Casimir effect and the behavior of black holes. Similarly, in string theory, the uncertainty principle plays a role in shaping our understanding of the fundamental nature of matter. String theory proposes that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings. The uncertainty principle is central to understanding how these strings behave and how they give rise to the particles we observe in the universe. In this framework, space and time themselves may emerge from the interactions of these strings, and the uncertainty principle provides a fundamental limit to how precisely we can measure the properties of these strings. Ultimately, Heisenberg's uncertainty principle has reshaped not only physics, but also our broader philosophical understanding of the universe. It forces us to confront the limits of human knowledge and to accept that uncertainty is a fundamental feature of the universe. The uncertainty principle suggests that, at the most basic level, the universe is not as neatly ordered and predictable as we once thought. Instead, it is governed by probabilities and uncertainty, and our understanding of it will always be constrained by the inherent fuzziness of quantum mechanics. In conclusion, the uncertainty principle remains one of the most profound and controversial ideas in the history of science. It challenges our classical intuitions about the nature of reality and forces us to rethink our assumptions about measurement, observation, and knowledge. Despite decades of research and experimentation, Heisenberg's uncertainty principle continues to be a cornerstone of quantum mechanics, and its implications resonate across a wide range of scientific disciplines. It is a reminder that the more we understand the universe, the more we realize how much we have yet to learn. In the quantum world, where uncertainty and probability reign supreme, understanding the true nature of particles becomes a matter of immense complexity. The very act of trying to comprehend the behavior of matter at the microscopic level requires a shift in how we think about reality. One of the crucial insights that arise from Heisenberg's uncertainty principle is the concept of superposition. This principle suggests that particles do not exist in one fixed state until they are observed. Instead, they exist in a combination of multiple possible states, each with a certain probability, until measurement collapses this superposition into a single state. This profound idea radically challenges the classical view of reality, where objects exist in a definite state at all times. To fully understand superposition, one must imagine a particle, such as an electron, as being both a wave and a particle at the same time. The particle can occupy multiple locations, moving through various possible paths with different probabilities, without ever being fixed in one position. This is a core feature of quantum mechanics, where the wave function, a mathematical function that describes the quantum state of a particle, represents all the possible locations and momenta the particle could have. Before measurement, the particle is not in any one state, but is spread out across all possible outcomes. The moment we measure it, the wave function collapses, and the particle assumes a specific position or momentum. This fundamental uncertainty in the position and momentum of particles, as highlighted by Heisenberg, extends far beyond mere measurements of these properties. The uncertainty goes deep into the heart of the quantum system itself, influencing not just our knowledge of the particle, but its actual behavior. Heisenberg's uncertainty principle and the concept of superposition emphasize that at the quantum level, certainty is an illusion, and the universe behaves in a far less predictable way than classical physics ever allowed. The uncertainty principle, combined with the idea of superposition, has led to what we now understand as quantum indeterminacy. This is a fundamental feature of quantum systems, where particles, before they are measured, can exist in multiple possible states simultaneously. While this is counterintuitive to our everyday experiences, it is experimentally confirmed through a variety of quantum experiments, including the famous double-slit experiment. In this experiment, particles like electrons or photons, when passed through a double slit, create an interference pattern on the other side, which is a signature of wave behavior. This happens even when particles are sent one at a time, suggesting that each individual particle behaves as if it passes through both slits at once, behaving as a wave and particle simultaneously. It is only when we attempt to measure which slit the particle went through that the interference pattern collapses, and the particle behaves like a particle, not a wave. This phenomenon, known as wave-particle duality, underlines the strange, counterintuitive nature of the quantum world. But it is the relationship between the wave function and the uncertainty principle that sets the stage for understanding the behavior of quantum systems. The wave function not only predicts where a particle is likely to be, but also provides us with probabilities, not certainties. The act of measurement is what collapses these probabilities into a single, observable outcome. Until measurement occurs, the particle exists in a superposition of all possibilities, existing everywhere and nowhere simultaneously. One of the most striking consequences of the uncertainty principle and the concept of superposition is the phenomenon known as quantum entanglement. Entanglement occurs when two or more particles become correlated in such a way that the state of one particle is directly related to the state of another, regardless of the distance between them. This means that the measurement of one particle's properties instantly determines the state of the other particle, even if they are light years apart. This seemingly spooky action at a distance, as Albert Einstein famously described it, challenges our classical notions of space and time. The entangled particles appear to communicate faster than the speed of light, defying the limitations imposed by relativity. Quantum entanglement was first described by Einstein, Podolsky, and Rosen in 1935 as part of what is known as the EPR paradox. The paradox arose from the realization that quantum mechanics, as described by the uncertainty principle and superposition, allowed for instantaneous correlations between particles, which seemed impossible according to the laws of classical physics. If quantum mechanics were complete, then these correlations would occur even across vast distances, violating the principle of locality and the speed of light limit. This was deeply troubling to Einstein and his colleagues, who believed in a deterministic, local reality. However, over the years, numerous experiments have confirmed the reality of quantum entanglement. The most famous of these experiments was carried out by physicist John Bell in the 1,960 seconds, resulting in what is known as Bell's theorem. Bell's theorem showed that the predictions of quantum mechanics were incompatible with any theory based on local hidden variables, that is, theories where the particles have predetermined states and information is not transmitted faster than the speed of light. The experimental tests of Bell's theorem have overwhelmingly supported the predictions of quantum mechanics, demonstrating that the world behaves as quantum theory suggests, not as classical physics would predict. Entanglement is now one of the cornerstones of modern quantum theory, with practical applications emerging in the fields of quantum computing, quantum cryptography, and quantum communication. In quantum computing, entanglement is harnessed to allow quantum bits, or qubits, to represent multiple states simultaneously, enabling vastly more efficient computation for certain types of problems. Quantum cryptography uses entanglement to create ultra-secure communication channels, as any eavesdropping on the entangled particles would collapse their wave function and be immediately detectable. The strange and counterintuitive nature of quantum mechanics continues to challenge our deepest intuitions about the nature of reality. While the uncertainty principle tells us that we can never have complete knowledge of a quantum system, quantum entanglement suggests that the very fabric of the universe is interconnected in ways that classical physics could never have imagined. The principle of non-locality, where particles can instantaneously affect each other, regardless of the distance separating them, defies our understanding of space and time. But perhaps one of the most significant philosophical implications of Heisenberg's uncertainty principle and the idea of superposition is how they force us to reconsider the concept of determinism. Classical physics, particularly Newtonian mechanics, assumed that the universe was a clockwork mechanism governed by precise laws that could predict the future if the present was known. However, quantum mechanics suggests that this deterministic worldview may be an illusion. Instead of a deterministic universe, quantum mechanics points to a probabilistic reality, where outcomes are not fixed but are spread out in terms of probabilities until they are measured. This shift from determinism to indeterminacy has far-reaching implications, not only for physics but also for our understanding of free will, causality, and the nature of existence itself. If the universe is inherently probabilistic, can we truly claim to have control over our actions? Is our sense of free will simply an illusion created by our inability to measure all the underlying factors that influence our decisions? These are deep philosophical questions that continue to provoke debate among scientists, philosophers, and theologians alike. In conclusion, the uncertainty principle and the concept of superposition have reshaped our understanding of the universe in profound ways. They challenge our classical intuitions and force us to embrace a world where uncertainty, probability, and interconnectedness reign. Heisenberg's uncertainty principle, in particular, highlights the limits of human knowledge and the role that observation plays in shaping the quantum world. Whether we are exploring the strange world of quantum entanglement or grappling with the philosophical implications of quantum indeterminacy, these concepts continue to challenge our deepest assumptions about reality. The quantum world may be uncertain, but it is this very uncertainty that provides a rich and fascinating playground for scientists and thinkers alike. As we dive deeper into the quantum world, it becomes increasingly clear that the principles governing this strange realm are vastly different from those of classical physics. Beyond Heisenberg's uncertainty principle and the concept of superposition, there lies another fascinating concept known as quantum tunneling, which has profound implications for understanding both the microscopic and macroscopic behaviors of the universe. Quantum tunneling is a phenomenon where particles pass through energy barriers that would be insurmountable in classical physics. This seemingly paradoxical behavior is a direct result of the probabilistic nature of particles in the quantum world and is intimately connected to the ideas of uncertainty and superposition. In classical physics, if a particle encounters a barrier that it doesn't have enough energy to surmount, it is reflected back. This is true for objects like baseballs, cars, or even planets. But in the quantum world, particles do not have definite positions or energies in the same way. Instead, they exist as waves of probability. This means that there is a finite probability that a particle can tunnel through a barrier, even if it doesn't have enough energy to overcome it classically. This behavior occurs because, according to the principles of quantum mechanics, particles like electrons do not have a single, fixed position. They are spread out as a probability wave, and this wave can extend through barriers, even though the particle itself is not classically capable of overcoming the barrier. Quantum tunneling is a crucial phenomenon in many physical processes. One of the most well-known examples is nuclear fusion, the process that powers the sun. In the core of the sun, hydrogen nuclei, protons, are subject to extremely high temperatures and pressures. Classical physics would predict that these protons should repel each other due to their positive charges, and that they would never come close enough to fuse. However, thanks to quantum tunneling, protons are able to tunnel through the electrostatic repulsion barrier, allowing them to collide and fuse, releasing vast amounts of energy. Without tunneling, nuclear fusion, and, by extension, life as we know it would be impossible. Tunneling is also a key principle behind the operation of modern technologies, such as scanning tunneling microscopes, which allow us to observe individual atoms. These microscopes exploit the ability of electrons to tunnel through a thin barrier, allowing them to interact with atoms on a surface in ways that were previously thought impossible. Quantum tunneling is also vital in understanding semiconductor devices, such as transistors, which are the building blocks of modern electronics. In these devices, electrons are able to tunnel through potential barriers, enabling them to flow through the material and perform the necessary functions of switching and amplification. This ability of particles to tunnel through barriers is, in a sense, a direct consequence of the principles of uncertainty and superposition. The probabilistic nature of particles allows them to exist in a superposition of states, meaning that they can occupy multiple positions simultaneously, even those that would be classically forbidden. The uncertainty in position and momentum that Heisenberg described allows for the possibility of tunneling to occur. When a particle is not confined to a single point in space but rather exists in a range of potential locations, the probability exists for it to leak through barriers, leading to phenomena like tunneling. This concept of tunneling also has a philosophical dimension, as it further challenges the classical notion of determinism. In classical physics, the future behavior of a system can be predicted with complete certainty if the initial conditions are known. In contrast, quantum mechanics tells us that particles behave probabilistically, and even though we may know the rules governing their behavior, we cannot predict the outcome of any single event with absolute certainty. This introduces an element of randomness into the fabric of reality, raising questions about the deterministic nature of the universe and the role of chance in shaping the future. In addition to tunneling, another critical aspect of quantum mechanics is the phenomenon of quantum entanglement, which has been one of the most perplexing and debated aspects of the theory. Entanglement occurs when two or more particles become correlated in such a way that the state of one particle is directly related to the state of another, regardless of the distance between them. Once particles are entangled, measuring the state of one particle instantaneously determines the state of the other, no matter how far apart the two particles are. This spooky action at a distance, as Albert Einstein called it, seems to defy the principles of locality, which state that objects can only influence each other through direct interactions that occur in their immediate vicinity. Entanglement was first described by Einstein, Podolsky, and Rosen in 1935 as part of what is known as the EPR paradox. They used this thought experiment to highlight what they saw as the paradoxical nature of quantum mechanics. According to the EPR paradox, quantum mechanics seem to allow for instantaneous communication between entangled particles, violating the principle of locality and the finite speed of light. Einstein, who had strong reservations about the completeness of quantum mechanics, believed that this was a sign that the theory was incomplete. He suggested that there must be hidden variables, unknown factors that determined the behavior of particles, restoring a deterministic view of the universe. However, decades of experiments have confirmed the validity of quantum entanglement, demonstrating that particles can indeed be instantaneously correlated across vast distances. The most famous experimental test of quantum entanglement was conducted by physicist John Bell in the 1,960 seconds, resulting in Bell's theorem. Bell showed that if quantum mechanics is correct, then any hidden variable theory that respects locality cannot reproduce the predictions of quantum mechanics. Subsequent experiments, such as those conducted by Elaine Aspect in the 1,980 seconds, provided overwhelming evidence that quantum entanglement is real and that it does indeed violate classical ideas of locality. This realization has profound implications for our understanding of space, time, and the nature of reality itself. If particles can influence each other instantaneously across vast distances, it challenges the very structure of the universe as we know it. The implications of entanglement have far-reaching consequences not just for physics, but for philosophy, as they force us to reconsider the nature of causality, information, and the fabric of space and time. Quantum entanglement has also opened the door to new technological advancements, particularly in the field of quantum computing. In a quantum computer, qubits, the fundamental units of quantum information, can exist in superposition, representing multiple values simultaneously. This ability to be in multiple states at once enables quantum computers to perform certain types of calculations exponentially faster than classical computers. Quantum entanglement plays a critical role in this process, allowing qubits to be entangled and share information in ways that are not possible with classical bits. Entanglement is also the foundation of quantum cryptography, which promises to revolutionize secure communication. Quantum cryptography uses the principles of quantum mechanics, including entanglement, to create unbreakable encryption systems. Any attempt to intercept or measure the entangled particles would disturb the system and reveal the presence of an eavesdropper, ensuring that communications remain secure. The development of quantum key distribution protocols, such as the BB84 protocol, relies on the properties of entanglement to guarantee the security of digital communications. As we explore the mysteries of the quantum world, we find that Heisenberg's uncertainty principle, superposition, quantum tunneling, and quantum entanglement all weave together to form a complex, interconnected framework that challenges our deepest assumptions about reality. These principles not only shape the behavior of particles, but also offer new insights into the nature of space, time, and information itself. Quantum mechanics, with its strange and counterintuitive ideas, continues to be one of the most profound and transformative fields of study in modern science. Ultimately, the insights provided by quantum mechanics and the principles of uncertainty, superposition, tunneling, and entanglement push us to rethink the very nature of reality. They show us that the universe is not a deterministic clockwork machine, but a probabilistic, interconnected system where uncertainty is intrinsic to the fabric of existence. This realization is not just a scientific breakthrough, it is a philosophical one, offering new perspectives on the nature of knowledge, reality, and the very limits of human understanding. At the heart of the quantum revolution is the strange and profound relationship between matter and energy. This relationship, once simply described by classical physics, is now understood to be much more complex, elusive, and intertwined with the very fabric of reality. The third keynote we must explore in this journey into quantum mechanics is the concept of quantum superposition, which introduces the notion that particles can exist in multiple states at once. This idea stands in stark contrast to the classical view of the world, where objects are assumed to exist in one definitive state at any given time. To grasp the full extent of quantum superposition, we must first unravel the connection between wave-particle duality, the behavior of light and matter, and the role of the observer. Quantum superposition is perhaps best illustrated by the famous double-slit experiment. This simple yet profound experiment involves sending particles, such as electrons or photons, through a barrier with two slits. When not observed, the particles behave as if they pass through both slits simultaneously, creating an interference pattern on a screen placed behind the barrier, much like waves of light or water interacting with each other. The interference pattern suggests that the particles are not behaving as individual entities but as waves spread out across the two slits, simultaneously occupying multiple positions. However, when the experimenters attempt to observe which slit the particle passes through by placing a detector at one of the slits, the interference pattern disappears and the particles behave like classical particles. The act of measurement causes the wave function of the particle to collapse, and the particle takes on a definite position. This shift from wave-like behavior to particle-like behavior is at the core of quantum mechanics and is a direct consequence of the principle of superposition. Before measurement, the particle is not confined to a single state. Instead, it exists in a superposition of all possible states, and the act of measurement collapses these possibilities into a single reality. The importance of superposition extends far beyond the realm of experimental physics. It is fundamental to our understanding of the nature of reality at the quantum level. The idea that particles can exist in multiple states simultaneously challenges our classical intuitions. In classical physics, if you were to look at an object like a ball, it would have a well-defined position and velocity at any given time. There would be no ambiguity about where it is or how fast it is moving. But in the quantum world, particles do not behave in this predictable manner. Instead, they exist in a cloud of probabilities, where their position and momentum are not fixed, but spread out across a range of possible outcomes. The wave function, a mathematical function that describes the state of a quantum system, encapsulates all of these possibilities. The wave function provides a complete description of the system, including the probabilities of finding a particle in various positions or with various momenta. This probabilistic nature of quantum mechanics was first formalized by Max Born, who interpreted the square of the wave function as representing the probability density for a particle's position. While the wave function gives us a complete description of a quantum system, it does not tell us precisely where the particle is at any given moment. Instead, it provides the probabilities of where the particle might be found if we were to measure it. This probabilistic nature of quantum mechanics was further highlighted by Werner Heisenberg's uncertainty principle, which states that there is a fundamental limit to how precisely we can know certain pairs of properties of a particle, such as its position and momentum, at the same time. The more precisely we try to measure one property, the less precisely we can know the other. The uncertainty principle reinforces the idea that in the quantum world, certainty is replaced by probability. The more we try to pin down the exact state of a system, the more elusive its precise behavior becomes. Quantum superposition is not just a curiosity of the microscopic world. It has profound implications for the development of technologies that are poised to revolutionize computing, communication, and cryptography. One of the most exciting areas where superposition plays a pivotal role is in the development of quantum computing. Unlike classical computers, which process information using bits that are either in a state of 0 or 1, quantum computers use quantum bits or qubits. A qubit can exist in a superposition of both 0 and 1 states simultaneously, thanks to the principle of superposition. This allows quantum computers to perform certain types of calculations much faster than classical computers. For example, in classical computing, if you wanted to find a specific piece of data in a large database, the computer would have to search through each entry, one by one. However, a quantum computer, leveraging the power of superposition, can explore all possibilities simultaneously, drastically reducing the time required for certain types of computations. This ability to perform parallel computations opens up new avenues for solving complex problems in fields ranging from cryptography to drug discovery. In addition to quantum computing, The phenomenon of superposition is also central to the field of quantum cryptography. One of the most important applications of quantum mechanics in cryptography is the development of quantum key distribution, QKD, a technique that uses the principles of quantum mechanics to create secure communication channels. In QKD, information is encoded onto quantum particles, and any attempt to eavesdrop on the transmission would disturb the quantum states of the particles, revealing the presence of the intruder. This provides a level of security that is impossible to achieve with classical encryption methods. Quantum superposition plays a crucial role in this process, as it allows for the creation of unbreakable cryptographic keys based on the principles of quantum mechanics. As we move from the realm of superposition to the concept of quantum entanglement, we enter even more profound territory. Entanglement is a phenomenon in which two or more quantum particles become correlated in such a way that the state of one particle is directly related to the state of another, even if the particles are separated by vast distances. Once entangled, the properties of the particles become intertwined, and measuring one particle's properties instantaneously determines the properties of the other particle, regardless of the distance between them. This spooky action at a distance, as Einstein called it, challenges our classical notions of locality and causality. Entanglement was first described by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 as part of what is now known as the EPR paradox. The paradox arose from the realization that quantum mechanics, as described by Heisenberg's Uncertainty Principle and superposition, allowed for instantaneous correlations between entangled particles. This seemed to violate the principle of locality, which states that objects can only influence each other through direct interactions in their immediate vicinity. Einstein, who was a firm believer in the principle of locality, rejected the idea of entanglement, calling it spooky action at a distance. However, later experiments, such as those conducted by John Bell in the 1960 seconds, confirmed the reality of entanglement, showing that quantum mechanics was correct and that particles could indeed be correlated across vast distances in ways that defied classical physics. Entanglement has profound implications for our understanding of the universe. It suggests that the properties of particles are not determined locally, but are connected to the larger quantum system in a non-local way. This challenges our classical ideas of space and time, where objects are thought to exist independently of one another. In the quantum world, the interconnectedness of particles means that the universe is much more interconnected than we might have imagined. Entanglement is not just a theoretical concept, it has practical applications in fields such as quantum computing, quantum cryptography, and quantum teleportation. In quantum computing, entangled qubits are used to perform computations in parallel, allowing for faster and more efficient processing of information. In quantum cryptography, entanglement ensures that any attempt to eavesdrop on a communication channel will be immediately detected, providing unbreakable security. Quantum teleportation, which involves the transfer of quantum information from one particle to another, relies on entanglement to transmit information instantaneously over long distances. The implications of quantum superposition and entanglement extend far beyond the realm of physics. These phenomena challenge our deeply held intuitions about the nature of reality, space, and time. They suggest that the universe is not as neatly ordered and predictable as we once thought, but is instead governed by uncertainty, probability, and interconnectedness. These principles of quantum mechanics force us to confront the limits of human knowledge and to accept that reality is far more complex than we can ever fully comprehend. As we continue to explore the mysteries of the quantum world, it becomes increasingly clear that the principles of quantum mechanics, superposition, entanglement, and uncertainty are not just abstract concepts, but are essential to understanding the very nature of the universe. The world around us may appear to be solid, predictable, and deterministic, but at the quantum level, It is a world of possibility, interconnectedness, and mystery. The strange behaviors of quantum mechanics, superposition, entanglement, and the inherent uncertainty represent only the beginning of our journey into understanding the quantum realm. As we delve deeper, one cannot overlook the significance of quantum coherence and decoherence, which serve as crucial concepts in bridging the microscopic quantum world with the macroscopic classical world we experience every day. Understanding these phenomena helps to explain how quantum systems, which are in superposition and entangled states, behave in ways that may seem completely out of place when compared to our intuitive understanding of the world. At the heart of quantum coherence is the idea that quantum systems, such as particles or atoms, can exist in a state of perfect synchronization or coherence, where their properties are linked together in a way that cannot be explained classically. When particles or quantum systems are coherent, they are capable of existing in superposition, and their properties are interdependent in ways that defy classical expectations. Quantum coherence is often referred to as the ability of a system to remain in a superposition of multiple states at once without collapsing into one definite state, allowing it to interact and evolve in ways that classical systems cannot. This coherence is what allows quantum systems to perform computations that classical computers could not achieve, particularly through quantum entanglement and superposition. For instance, a quantum computer uses qubits that, due to quantum coherence, can perform multiple calculations simultaneously, greatly enhancing the computational power. However, this state of coherence does not last forever. Eventually, quantum systems become decoherent as they interact with their environment, which leads to the collapse of their superposition and entangled states. Quantum decoherence is the process by which a quantum system loses its coherence, transitioning from a superposition of possible states to a single classical state. This process happens when quantum systems interact with their environment in ways that disturb the delicate balance of superposition, causing the quantum system to behave more like a classical system with definite properties. Decoherence is responsible for the transition from the quantum world, which is governed by probabilities, to the classical world we experience, where objects appear to have definite positions, velocities, and other properties. The phenomenon of decoherence has significant implications for quantum technologies, such as quantum computing. In quantum computing, qubits are extremely sensitive to their environment, and even the smallest interaction with the surroundings can cause them to decohere and lose their ability to perform quantum computations. This presents a major challenge in the development of practical quantum computers. Scientists and engineers are working to isolate qubits from their environment, using techniques like quantum error correction and quantum isolation to prevent decoherence from disrupting the system. The study of quantum coherence and decoherence also sheds light on the classical quantum divide, which has been one of the most puzzling aspects of quantum mechanics. The transition from the probabilistic quantum world to the deterministic classical world is often referred to as the measurement problem. In classical physics, we assume that objects exist in a definite state whether or not we observe them, and this is true for macroscopic objects in our everyday experience. However, in quantum mechanics, the system only decides on a particular state once it is measured, and until that moment, it exists in a superposition of all possible states. This leads to a fundamental question: at what point does a quantum system transition from being in a superposition of states to a definite classical state? Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that the act of measurement itself causes the collapse of the wave function, the mathematical representation of the superposition into one definite state. Other interpretations, such as the many worlds interpretation, propose that all possible outcomes occur simultaneously, but in different branches of the universe, where each outcome is realized in a separate parallel world. While these interpretations differ in their philosophical implications, they all aim to address the same fundamental question: how does the quantum world give rise to the classical world we observe? Decoherence plays a key role in answering this question by offering a mechanism through which the quantum system interacts with its environment, causing the superposition to collapse into one of the possible classical states. In this view, decoherence explains why macroscopic objects behave according to classical laws, even though they are made up of quantum particles. However, the debate is far from settled, as some physicists argue that decoherence alone is not sufficient to explain the transition to classicality, and that a more fundamental theory of measurement is still needed. Another fascinating aspect of quantum mechanics that has far-reaching implications is the phenomenon of quantum teleportation. Quantum teleportation is the process by which quantum information, such as the state of a particle, is transferred from one location to another without physically moving the particle itself. This is achieved through the use of entanglement, where two particles are entangled in such a way that the state of one particle is directly linked to the state of the other, regardless of the distance between them. When one of the entangled particles is measured, the state of the other particle is instantly determined, even if it is light years away. Quantum teleportation does not involve the actual transmission of matter, but rather the transfer of quantum information. The process relies on the entanglement of particles, and when the state of one particle is measured, the information is teleported to the other particle. This phenomenon was first demonstrated experimentally in 1993 by Charles Bennett and his colleagues, who successfully teleported quantum information between two particles separated by a distance. While quantum teleportation is still in its infancy and has not yet been applied to large-scale systems, it holds tremendous potential for revolutionizing communication and computing. Quantum teleportation could have profound implications for secure communication systems. If quantum teleportation could be scaled up to transmit information over long distances, it could provide the foundation for ultra-secure communication networks that are completely immune to eavesdropping. This is because any attempt to intercept the quantum information would disturb the system and immediately reveal the presence of the intruder. As a result, quantum teleportation could pave the way for unbreakable encryption systems that would provide a level of security far beyond what is possible with classical cryptography. Moreover, the concept of quantum teleportation opens up the possibility of transmitting quantum information over vast distances, potentially enabling the creation of a quantum internet. In a quantum internet, quantum information could be transmitted securely between distant locations with the help of quantum entanglement and teleportation. Such a system could dramatically improve the speed and security of communications, making it an essential tool for future technologies in fields ranging from cybersecurity to artificial intelligence. The profound implications of quantum mechanics extend beyond technology. Quantum mechanics has also influenced our philosophical understanding of the nature of reality. The idea of a probabilistic universe, where outcomes are not determined until they are measured, challenges our classical assumptions about determinism and causality. It forces us to reconsider the very nature of existence itself. If the universe is fundamentally probabilistic, then perhaps there is no definitive reality until it is observed. This leads to deep questions about the role of the observer in the creation of reality and about the true nature of time and space. Moreover, quantum mechanics has inspired new ways of thinking about consciousness and the mind. Some scientists and philosophers have proposed that quantum mechanics may play a role in the functioning of consciousness, suggesting that the mind could be a quantum system in itself. This idea, though controversial, has sparked renewed interest in the intersection between quantum theory and the philosophy of mind. The possibility that consciousness itself might be linked to quantum processes challenges our classical views of the mind, and opens up exciting avenues for future research. In conclusion, the phenomena of quantum coherence, decoherence, and teleportation provide a window into the strange and mysterious world of quantum mechanics. These phenomena highlight the fundamental differences between the quantum and classical worlds and challenge our classical intuitions about the nature of reality. As we continue to explore the quantum realm, we are confronted with profound questions about the nature of existence, the role of the observer, and the very limits of human knowledge. Quantum mechanics not only revolutionizes our understanding of the universe but also inspires new philosophical, technological, and metaphysical questions that will shape the future of science and humanity. As we continue to explore the landscape of quantum mechanics, we inevitably encounter the role of quantum measurement, which plays a pivotal part in how we understand the interaction between the quantum and classical worlds. Measurement in quantum mechanics is unlike anything we experience in the classical world. In classical physics, measurement is a straightforward process where the observer can measure the properties of a system without influencing the system itself. However, in quantum mechanics, measurement is far more complex and has profound implications for the nature of reality itself. The most striking feature of quantum measurement is the concept of wave function collapse. The wave function is a mathematical representation of a quantum system state, encompassing all the possible outcomes that could occur when a measurement is made. Prior to measurement, a quantum system, such as an electron or photon, exists in a superposition of all possible states. For instance, a particle may be in a superposition of being at multiple locations at once or having multiple energies. It is only when a measurement is made that the wave function collapses and the particle takes on a definite state. This collapse is not a gradual process but an abrupt one, where all the probabilities described by the wave function are reduced to a single outcome. This idea challenges our classical understanding of measurement, where we assume that objects exist in definite states independent of whether or not we observe them. In the quantum world, however, it is the act of measurement that forces a system to assume a definite state. The measurement problem, as it is known, raises deep philosophical and scientific questions about the nature of reality. Does the act of observation cause reality to come into existence, or is there an objective reality independent of observation? This is a central debate in the interpretation of quantum mechanics. One of the most famous thought experiments exploring the implications of quantum measurement is Schrödinger's cat paradox. Schrödinger proposed a scenario in which a cat is placed inside a sealed box with a device that has a 50% chance of releasing poison, depending on the state of a radioactive atom. According to quantum mechanics, before the box is opened and the system is measured, the radioactive atom is in a superposition of decayed and non-decayed states, and the cat is simultaneously alive and dead. This paradox illustrates the strange nature of quantum measurement. The cat's fate is entangled with the quantum state of the atom, and only when the system is observed does the superposition collapse into a definite outcome, either alive or dead. While Schrödinger's cat is an exaggerated thought experiment, it highlights the tension between the quantum and classical worlds. At the microscopic scale, particles exist in a superposition of all possible states, but as objects become larger and more complex, they appear to behave according to classical physics, with definite properties and outcomes. This transition from the quantum to the classical is one of the central puzzles of quantum mechanics. It raises questions about why the weirdness of quantum mechanics is not observed in our everyday experience. Why don't we see cats that are both alive and dead, or coins that are both heads and tails, until we look at them? One explanation comes from the concept of decoherence, which suggests that quantum systems, when interacting with their environment, lose their ability to maintain a superposition of states and behave classically. Decoherence explains why macroscopic objects like cats, cars, or planets don't appear to be in superpositions, As the system interacts with countless particles in its environment, the superposition collapses into a classical state. However, decoherence does not fully solve the measurement problem, as it does not provide a clear mechanism for the collapse of the wave function itself. It simply explains why certain quantum effects are not observed in the macroscopic world. This brings us to the various interpretations of quantum mechanics that attempt to explain the nature of quantum measurement. The Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg, suggests that the wave function collapse is a fundamental process that occurs when a system is measured. According to this interpretation, the wave function represents the probabilities of different outcomes, and measurement causes these probabilities to collapse into a definite result. However, other interpretations, such as the many worlds interpretation, propose that all possible outcomes of a measurement actually occur, each in a separate, parallel universe. According to this view, there is no collapse of the wave function, and the universe simply splits into different branches, each corresponding to a different outcome. These different interpretations highlight the deep mystery at the heart of quantum mechanics. Measurement is not simply a passive process, but one that plays an active role in determining the state of the system. The observer, or the act of observation, seems to shape the reality of the system, suggesting that reality itself may not be as objective and independent as we once believed. The implications of quantum measurement go beyond the realm of physics and touch on profound philosophical questions about the nature of existence, the role of the observer, and the limits of human knowledge. As we continue to study quantum mechanics and its paradoxical behaviors, we are faced with a universe that defies our classical intuitions and challenges our very understanding of what it means for something to exist. Ultimately, quantum measurement is a concept that lies at the heart of the quantum revolution. It forces us to reconsider the fundamental nature of reality and our place within it. As our understanding of quantum mechanics evolves, so too does our understanding of the universe and our role as observers. Whether through wave function collapse, decoherence, or the many worlds interpretation, the act of measurement in quantum mechanics opens up a world of possibilities, leading us to new insights into the very fabric of existence. As we explore the intricate workings of quantum mechanics, one of the most mind-bending and revolutionary aspects is the phenomenon of quantum entanglement. This strange and profound concept suggests that particles can become correlated in such a way that the state of one particle is directly tied to the state of another, regardless of the distance between them. This instantaneous connection, often referred to as spooky action at a distance, challenges our classical notions of space, time, and causality. Quantum entanglement arises when two or more particles interact in a way that causes their properties to become linked, so that the state of one particle is directly related to the state of another. Once entangled, these particles no longer behave as independent entities. Rather, they form a system where the properties of one particle can no longer be described without reference to the other. For instance, if two particles are entangled in terms of their spin, measuring the spin of one particle will instantly determine the spin of the other, no matter how far apart they are. This instantaneous correlation between particles occurs without any physical signal being exchanged between them, seemingly defying the speed of light limit established by relativity. The idea of entanglement was first introduced by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 in what is now known as the EPR paradox. The EPR paradox was designed to challenge the completeness of quantum mechanics. Einstein and his colleagues believed that quantum mechanics, as it was understood at the time, implied non-locality, a concept that seemed incompatible with the theory of relativity, which holds that information cannot travel faster than the speed of light. In the EPR paradox, they proposed a thought experiment in which two particles, once entangled, could instantaneously influence each other, even if they were light years apart. This, Einstein argued, was a sign that quantum mechanics could not be the full story, and that there must be hidden variables or additional factors at play. However, quantum mechanics, as it is currently understood, does not support the existence of hidden variables. In the 1960 seconds, physicist John Bell formulated Bell's theorem, which provided a way to test the predictions of quantum mechanics against those of hidden variable theories. Bell showed that if hidden variables existed, they would produce results that were different from those predicted by quantum mechanics. Subsequent experiments testing Bell's theorem have overwhelmingly supported the predictions of quantum mechanics, confirming that entanglement is indeed a real phenomenon, and that particles can instantaneously influence one another over vast distances without violating the principles of relativity. This realization has profound implications for our understanding of the universe. It suggests that space, as we conceive it, may not be as continuous and separated as we once thought. Instead, quantum mechanics hints at a deeply interconnected reality, where particles are not isolated entities, but are part of a broader, non-local system. This non-locality challenges the traditional view that the universe is made up of independent objects that interact only when they come into direct contact. Instead, quantum mechanics paints a picture of a universe where the boundaries between objects are not so well defined and where particles can be interconnected in ways that transcend the limitations of classical space. Entanglement has been experimentally confirmed in a variety of experiments, the most famous being the entanglement swapping experiment. In this experiment, particles that have never interacted can still become entangled through a process called quantum entanglement swapping. This means that entanglement does not need to be directly established between two particles that are in contact with each other. Instead, it can be mediated through intermediate particles, further demonstrating the non-local nature of quantum mechanics. One of the most exciting implications of quantum entanglement is its potential applications in technology. Quantum entanglement is at the heart of quantum computing, a field that promises to revolutionize computation. In quantum computers, qubits, which are the quantum analog of classical bits, can exist in multiple states simultaneously due to superposition. Moreover, entangled qubits can be used to perform calculations that are exponentially more efficient than classical computers, particularly for certain complex problems, such as cryptography, material science, and optimization. Quantum computers exploit entanglement to link qubits in ways that classical computers cannot replicate, enabling massive parallel computations that would otherwise be impossible. Entanglement also has significant implications for quantum communication, particularly in the realm of quantum cryptography. One of the key applications of entanglement in cryptography is quantum key distribution, QKD, which allows for the secure exchange of cryptographic keys. QKD relies on the principles of quantum mechanics, including entanglement, to ensure that any attempt to eavesdrop on the communication would disturb the quantum states of the particles being exchanged. This disturbance would be immediately detectable, making it impossible for a third party to secretly intercept the key without being noticed. This level of security is far beyond anything that can be achieved using classical encryption methods. Furthermore, entanglement plays a crucial role in the emerging field of quantum teleportation. Quantum teleportation allows for the transfer of quantum information between particles over vast distances without the need to physically move the particles themselves. This phenomenon relies on entanglement to transmit the quantum state of one particle to another, effectively teleporting the information. While this process has been experimentally demonstrated over short distances, the potential applications of quantum teleportation could be transformative for communications and data transfer in the future, enabling ultra-secure high-speed communication channels. The deep interconnection between entangled particles, despite their separation in space, raises profound philosophical questions about the nature of reality, information, and the role of the observer. The non-local nature of entanglement challenges our classical views of causality, where events are expected to be connected by physical processes that occur through time and space. Entanglement suggests that information can be transmitted instantaneously, challenging our traditional understanding of the flow of time and the nature of causality itself. It raises questions about the limits of knowledge and the very fabric of reality, as it implies that the universe may be far more interconnected and holistic than we previously understood. In conclusion, quantum entanglement is one of the most fascinating and perplexing phenomena in quantum mechanics. It challenges our understanding of space, time, and causality, offering a glimpse into a deeper, non-local reality. Its experimental confirmation has not only solidified quantum mechanics as a cornerstone of modern physics, but also opened up new possibilities for revolutionary technologies such as quantum computing, quantum cryptography, and quantum teleportation. As we continue to unravel the mysteries of entanglement, we are confronted with a universe that is interconnected in ways we are only beginning to understand. As we continue to explore the fundamental concepts that shape quantum mechanics, one of the most perplexing and crucial phenomena is quantum tunneling. This process occurs when particles, such as electrons or protons, pass through potential barriers that they classically should not be able to overcome. In classical physics, if a particle doesn't have enough energy to surmount a barrier, it simply cannot pass through. However, quantum mechanics defies this expectation. Thanks to the probabilistic nature of particles at the quantum level, tunneling allows particles to leak through barriers, even when they do not have enough energy to surpass them, offering a glimpse into the strange and counterintuitive world of quantum reality. The phenomenon of tunneling arises from the wave-like nature of particles in quantum mechanics. According to quantum theory, particles like electrons are not localized to a single position, but are instead described by a wave function that represents the probability of finding a particle in a particular location. This wave function extends beyond the physical boundaries of a particle's position, and, in some cases, it can spill over a barrier, meaning there is a non-zero probability of the particle being found on the other side of the barrier, even though classically it doesn't have enough energy to escape. In essence, the wave function gives particles the potential to exist in places they seemingly shouldn't be able to reach, due to the probabilistic cloud around them. This ability of particles to tunnel through energy barriers is not just an abstract curiosity, but a fundamental process that underpins many natural phenomena. One of the most notable examples is nuclear fusion in stars, including our Sun. In the core of the Sun, hydrogen nuclei, protons, collide with one another under extreme conditions of temperature and pressure. According to classical physics, the protons should repel each other due to their positive charges, making it highly improbable for them to fuse. However, due to quantum tunneling, protons are able to bypass the electrostatic barrier created by their mutual repulsion and collide, eventually fusing to form helium and releasing massive amounts of energy. Without tunneling, the energy required for nuclear fusion would be so great that stars, including the Sun, could never sustain the fusion process. Tunneling also plays a vital role in modern technologies, particularly in the field of semiconductors and electronics. In these devices, such as transistors and diodes, quantum tunneling is essential for the flow of current. When electrons move through semiconductor materials, they can tunnel through thin layers of insulating material, allowing the transistor to function as an electronic switch. This tunneling effect is central to the operation of many devices that power our daily lives, from smartphones to computers. In addition to its importance in nuclear fusion and electronics, tunneling is also a key feature in the emerging field of quantum computing. In quantum computers, qubits, the quantum analog of classical bits, are used to store and process information. These qubits can exist in superposition, meaning they can represent both 0 and 1 at the same time. In some quantum computing algorithms, tunneling is used to search through large computational spaces by allowing the system to tunnel through potential solutions instead of processing each one sequentially. This enables quantum computers to potentially solve certain types of problems much faster than classical computers. Quantum tunneling also has profound implications for the philosophical and conceptual understanding of time and space. In the classical view, space and time are rigid and deterministic, with events unfolding in a linear, predictable manner. However, quantum mechanics, particularly phenomena like tunneling, suggests that particles do not follow a deterministic path. Instead, their behavior is probabilistic, governed by the wave function and influenced by their interactions with the surrounding quantum field. This raises intriguing questions about the nature of reality itself, suggesting that the classical ideas of fixed barriers and boundaries may not apply at the quantum level. The ability of particles to tunnel through seemingly impenetrable barriers implies a more fluid and interconnected view of the universe, where the traditional limitations of space and time do not always hold true. In addition to the philosophical implications, quantum tunneling challenges the conventional notion of causality. In classical physics, we assume that events unfold in a cause and effect relationship, with one event directly leading to another. However, in the quantum world, tunneling introduces an element of randomness and unpredictability. A particle does not have to go around a barrier or build up enough energy to surpass it. Instead, it simply appears on the other side, without following the predictable cause and effect process that we expect in classical systems. This probabilistic nature of quantum mechanics leads to a re-evaluation of how we perceive causality, pushing us to think beyond deterministic models and consider a universe where outcomes are based on probabilities rather than certainties. While quantum tunneling might seem like an abstract concept confined to the microscopic realm, its effects are felt at both the quantum and macroscopic scales. It influences the behavior of particles, atoms, and molecules, and plays a critical role in processes like radioactive decay, chemical reactions, and the functioning of the sun itself. Moreover, the principles of tunneling are becoming increasingly important in the development of new technologies, from quantum computers to advanced materials. As our understanding of quantum mechanics continues to deepen, it is likely that tunneling will play an even greater role in shaping future scientific and technological advancements. In conclusion, quantum tunneling is one of the most fascinating and essential phenomena in quantum mechanics. It defies classical expectations and offers profound insights into the nature of reality, from enabling the nuclear fusion process that powers stars to advancing cutting-edge technologies like quantum computing and semiconductors. Tunneling demonstrates the extraordinary and often unintuitive behavior of particles at the quantum level. Its implications stretch beyond science and technology, prompting deep questions about the nature of space, time, causality, and the very fabric of the universe. As we continue to explore the quantum realm, tunneling will undoubtedly remain a cornerstone of our understanding of the universe's deepest workings. In the vast, complex world of quantum mechanics, one phenomenon stands out for its challenge to classical intuition: quantum interference. At first glance, interference is typically associated with the behavior of waves, such as sound or light. Waves interact with each other in various ways. Sometimes they reinforce one another, and other times they cancel each other out. But in quantum mechanics, interference takes on a much deeper significance, especially when it comes to particles like electrons and photons. The core of quantum interference lies in the wave-like nature of particles, where the potential for interference arises from the overlapping wave functions of different quantum states. Quantum interference is most famously demonstrated in the double-slit experiment, which remains one of the most important experiments in quantum mechanics. When particles, such as electrons or photons, are fired through two closely spaced slits onto a detection screen, they do not simply form two patterns as one might expect from classical particles. Instead, they create an interference pattern similar to what one would see when water waves pass through two slits. This interference pattern is the result of the overlapping wave functions of the particles, which interfere with each other, either reinforcing or canceling each other out, depending on the relative phase of the waves. The key point here is that the interference pattern emerges even when particles are sent one at a time, suggesting that each particle, in its quantum state, is behaving as a wave spread across space and not as a localized particle. When no attempt is made to measure or observe which slit the particle passes through, the particle behaves as though it has passed through both slits simultaneously, creating an interference pattern. This is the quintessential demonstration of quantum superposition particles existing in a mixture of all possible states. However, when we try to measure which slit the particle passed through, the interference pattern disappears, and the particle behaves like a classical particle, passing through only one slit. The act of measurement, or observation, collapses the superposition into a single state, and the interference pattern vanishes. This phenomenon raises deep questions about the role of the observer in quantum mechanics, as it appears that the simple act of observation can fundamentally alter the behavior of particles. Quantum interference isn't just a theoretical curiosity, it has profound implications for both the nature of reality and the development of future technologies. One of the most important applications of quantum interference is in the field of quantum computing. In classical computing, bits represent information as either a 0 or a 1. However, in quantum computing, qubits, quantum bits, can represent both 0 and 1 simultaneously, thanks to the phenomenon of superposition. By utilizing quantum interference, quantum computers can exploit these superpositions to perform computations exponentially faster than classical computers for certain types of problems. The ability to harness quantum interference for calculations is one of the main reasons why quantum computers have the potential to solve complex problems like optimization, simulation, and cryptography much more efficiently than their classical counterparts. Another critical application of quantum interference is in quantum cryptography, particularly in the development of quantum key distribution, QKD. Quantum key distribution takes advantage of the principles of quantum mechanics to create secure communication channels. The most famous QKD protocol, BB84, uses the principles of quantum interference to ensure that any attempt to eavesdrop on the communication disturbs the quantum states of the particles being exchanged. Since quantum interference relies on the wave nature of particles, any measurement or interference caused by an eavesdropper will collapse the state of the system and reveal the intrusion. This ensures a level of security that is virtually impossible to achieve with classical encryption methods. Quantum interference also extends to the study of fundamental particles and their interactions in particle physics. At high-energy particle colliders, such as the Large Hadron Collider, LHC, quantum interference plays a key role in the analysis of particle collisions. Interference patterns help physicists detect and analyze particles that might otherwise go unnoticed. By studying the ways in which particles interfere with one another, physicists can better understand the underlying forces that govern the interactions of matter at the subatomic level. Moreover, quantum interference offers new insights into the nature of space and time. The wave-like behavior of particles, as demonstrated by interference, challenges the classical idea that particles are discrete objects with definite locations and trajectories. Instead, quantum mechanics suggests that particles are governed by probabilities, and their existence is spread out in a wave function. This realization forces us to reconsider our understanding of space as a fixed stage on which events unfold. In the quantum world, space and time are not as rigid as we once thought, and the relationships between particles are governed by non-locality and interconnectedness, as revealed by quantum interference and other phenomena like entanglement. The philosophical implications of quantum interference are profound, as it forces us to confront the limits of human observation and understanding. In classical physics, we assume that the world exists independently of our observation of it, that objects have definite properties whether we are observing them or not. But in quantum mechanics, interference patterns, which arise from the superposition of multiple possibilities, suggest that the act of measurement itself plays a central role in determining the outcome of a system. This brings into question the nature of reality and the role of consciousness in shaping the physical world. Are the probabilities described by quantum mechanics a reflection of an objective reality, or do they depend on the observer? These questions have sparked extensive debates in both the scientific and philosophical communities. In conclusion, quantum interference is one of the most fascinating and important phenomena in quantum mechanics. It provides a window into the strange, probabilistic world of quantum particles, where waves and particles coexist in a delicate balance. The interference patterns observed in experiments, like the double-slit experiment challenge, are classical notions of reality and offer profound insights into the interconnectedness of the quantum world. The applications of quantum interference in fields like quantum computing, cryptography, and particle physics are not just theoretical, they are shaping the future of technology. As we continue to explore the implications of quantum interference, we are forced to reconsider the very nature of space, time, and reality itself, opening new doors to understanding the universe at its most fundamental level.